This is our fourth topic in the discussion of kinetics. This will be a multi-video topic. This is on what is called reaction mechanisms, and this will be the start of the discussion. Now, it turns out that reactions can have more than one step to get to the final reaction. Each step is called an elementary reaction. You put together the elementary reactions to get the overall reactions, and that is called a proposed reaction mechanism. First, you propose the mechanism, then you run tests to see if that mechanism is correct. Now, there are two requirements for a proposed reaction mechanism if it's going to be considered a possibility or valid. The first is when you add up the steps, you must end up with the overall reaction that you know is going to occur. The second is the differential rate law, which is derived from the proposed mechanism, must be identical to the experimentally observed rate law. If either one of those does not happen, then the proposed mechanism is not plausible. In this video, we're going to deal predominantly with the first topic. The next video will deal with the second topic. Now, there can be more than one valid proposed mechanism. It then requires experimental proof to determine which valid proposed mechanism is the actual mechanism. And just for the record, a reaction mechanism can consist of one step. So let's take a generic chemical reaction, A2 plus B2 equals 2AB. Let's come up with a proposed mechanism. In the first step, the A2 separates to form two A particles. An A particle then reacts with a B2 molecule to form AB2. AB2 then reacts with the other A to form 2AB. Now, you should observe that the A to the right of the arrow here is canceled by the A to the left of the arrow here. This A on the right of the arrow is canceled by this A on the left of the arrow. And this AB2 to the right of the arrow is canceled by this AB2 to the left of the arrow. So when I add things up, those wipe each other out, and I end up with A2 plus B2 equals 2AB. That is the reaction I'm looking for. I have met the first requirement. Now, those chemicals that are crossed out are called reaction intermediates or just intermediates. They are usually short-lived species that get made and used up during the reaction. Now, we talk about what is called the molecularity of the elementary steps. The molecularity is defined as the number of reactant particles involved in an elementary step. So if we look at our generic reaction, in step 1, we see there is one A2 to the left of the arrow. That is called unimolecular. Here on step 2, we see there are two particles to the left of the arrow, so that's called bimolecular. For step 3, there are also two particles to the left of the arrow. That is also bimolecular. So step 1 is unimolecular. Steps 2 and 3 are both bimolecular. Now, if you were to have three particles on the reactant side, you would call it termolecular. But termolecular elementary reactions are very rare, and you never have a reaction with four molecules. This all comes back to collision theory. What are the odds that three particles will hit each other at exactly the right moment, with exactly the right kinetic energy to allow bonds to be broken, with exactly the right orientation? And the answer is really, really low. The chance of four molecules doing that is virtually zero. Now, the overall rate law for the equation is not dependent upon stoichiometry, but for an elementary reaction, it does come from the stoichiometry. Basically, you take the concentration of the reactants, are raised to the power of their coefficient in the rate law. Going back to our generic reaction, step 1 is unimolecular, and we would say the rate for that elementary step is rate equals K, the concentration of A sub 2. For step 2, which is bimolecular, the rate equals K, the concentration of A times the concentration of B2. And in a similar manner, for step 3, the rate is equal to the concentration of the AB2 times the concentration of A. The summation of the superscripts in the rate law should equal the molecularity of the elementary step. So the general rule is if you have A becomes product, it's unimolecular, and the rate is K times the concentration of the reactant. If you have 2A becomes product, this is bimolecular, and the rate equals K times the concentration of A squared. A plus B is bimolecular, And this is the rate law you get if you have 3A becomes product, that is termolecular, and you now have rate equals K, the concentration of A cubed. You could also have 2A plus B becomes product. This is also termolecular, so this would be the rate law. But do remember, the latter two are exceedingly rare. So let's apply this to a general equation. Here is a simple decomposition reaction. A mechanism is proposed. The proposed mechanism is this. 3 questions are to be answered. When you add up the steps, do you get the correct overall reaction? What is the molecularity for each step? And what is the rate law for each step? So let's answer the first question first. Here are the 2 steps. We see that the chlorines are intermediates. They cancel out. So when you add it up, you get this equation, which is the same as that equation. So the answer to this question is yes. Knowing that, we go on to the second question. What is the molecularity for each step? For step 1, we see there is one thing there, so it is unimolecular. For the second step, we see there are 2 compounds, so it is bimolecular. So now we've answered that question. On to question number 3. What is the rate law for each step? Well, for step 1, it would be rate equals K times the concentration of the reactant. And for step 2, the rate equals K times the concentration of each reactant. So that answers the questions. So to review, reactions might require more than one step, but they could only have one step. We call each step an elementary reaction. You propose a mechanism, then you test it. When you test it, there are 2 requirements for it to be valid. When you add up the elementary reactions, you must end up with the overall reaction. And the proposed differential rate law must be identical to the experimentally observed rate law. There can be more than one possible proposed reaction mechanism. If you have multiple steps, there will be chemicals which cancel out when you add things up. Those are called reaction intermediates or intermediates. We define the molecularity as the number of particles of reactants. If you have 1 particle, unimolecular, 2 particles bimolecular, 3 particles termolecular, which is exceedingly rare. The rate law for the elementary reaction is determined from the elementary reaction stoichiometry. Unlike the overall reaction rate, which may not be dependent upon stoichiometry. You're just going to raise the concentration of the reactant to the power of its coefficient. And so looking at that table again, you end up with, if it's unimolecular, it looks like this. There are 2 versions of bimolecular. They would look like this. There are 3 versions of termolecular. I'm just going to show you 2, because you could have A plus B plus C equals product. And in any case, those are all exceedingly rare. So that's the introduction to reaction mechanisms. In the next video, we're going to tackle how do you compare proposed rate laws to actual rate laws.